In this chapter, we're going to start looking at some of the basic concepts of graph theory. Our objectives for this section are to define basic graph theory terms. We will look at how to represent relationships with graphs, how to decide if two graphs are equivalent, how to recognize features of graphs, and how to apply graph coloring. So let's dive in. Let's say that it's time to plan that big spring break trip you've been just living for, and the first step is to get to South Padre Island. There's a pretty good chance that you're not going to find a flight directly from the nearest airport to Brownsville, Texas, which is the airport closest to South Padre. Instead, you'll need to make one or more intermediate connections to reach your final destination. I'm sure there's a metaphor for life in there somewhere. Graph theory is used to study problems like how to arrange connections that most efficiently get you to something like spring break nirvana. In this section, we will study the basic concepts that we need to learn about this useful branch of math. The graphs that we will study in this chapter are different from the graphs of equations and functions we've worked with previously. Rather than representing relationships between two variables, these graphs will be used to illustrate relationships between things like people, cities, and streets. It begins with a new definition of the word graph, which is used throughout the study of graph theory. So let's define a few terms here. A graph consists of a finite set of points called vertices. Singular there would be vertex, and line segments or curves called edges connecting the points. Here's a figure that shows an example of a graph. So in our notation, we will always draw vertices as black dots. In this case, they're labeled A, B, C, and D. The edges are A, B, B, C, C, D, D, A, A, C, and B, D. Since there is no vertex indicated at the intersection of edges AC and BD right here, it is assumed that the lines are not connected. You can think of it as two wires that are not joined together or two pipes that are not connected, one pipe passing over the other pipe. The graph in this figure also contains a loop. A loop is an edge that begins and ends at the same vertex. So that would be right here, the edge that begins and ends at vertex C. Graphs can be used to model a wide variety of situations. Cities on a map, floor plans for houses, border relationships of states or counties, even friendships or family relationships between people. In the next few examples 1 through 4, and really throughout the remainder of this chapter, we will use graphs to illustrate some of these situations. Let's look at our first example, this one representing islands with a graph. So we have this picture of 4 different islands, and the islands have various bridges connecting them. So we're asked to represent the islands and the bridges shown in the figure with a graph. Describe what you chose to be vertices and what you chose as edges in Y. Okay. In a graph, edges are lines or curves that connect the vertices. So the natural choice here would be to represent the islands with vertices and the bridges connecting them with edges. There are 4 islands. We will use A to represent Alpha Alpha Key, B to represent Blackbird K, C to represent Canary Island, and D to represent Duck Island. Let's take each island one at a time, starting with Alpha Alpha Key. Alpha Alpha Key has a bridge to Duck Island, so we'll put an edge there. Alpha Alpha Key has a bridge to Canary Island, so we'll put a bridge there. And then Alpha Alpha Key has a bridge to Blackbird K, So we'll put a bridge there. Let's move over here to Blackbird Cay. Blackbird Cay has a bridge to Alpha Alpha Key, which we already have drawn in. It also has a bridge to Canary Island. Draw that in. And then Blackbird Cay also has a bridge to Duck Island. So we will draw that in. All right. Canary Island has a bridge to Alpha Alpha Key, which we've already drawn in, a bridge to Blackbird Cay, which we've already drawn in, and another bridge to Duck Island, which we will draw in right here. And then Duck Island has a bridge to Alpha Alpha Key, which we have here, Canary Island, which we have here, and Blackbird Cay, which we have right here. So this is our graph representing this set of islands and bridges over here. Okay. Let's look at our next example, representing a floor plan with a graph. So we want to represent the floor plan of the house shown in this figure by a graph. Explain your choices for vertices and edges. In a graph, the edges connect the vertices, so we need to think about what in the floor plan connects things. That would be the doorways, right? The doorways are what connect the various rooms together. So we'll make the rooms vertices, and the doorways will be represented by edges. So let's do this. Let's do O for outside, L for living room, K for kitchen, D for dining room. Sorry, that's a lousy D. Let's try again. And B for bathroom. Okay, so let's take each room one at a time and figure out what doorways each room has and sketch those in as edges. Starting with the living room. The living room has a doorway to the outside. There's one edge. The living room has a doorway to the dining room. There's another edge. The living room has a doorway to the kitchen. There's the other edge. Okay. Let's move down to the dining room. The dining room has a doorway to the living room, which we already have, and a doorway to the bathroom. And the dining room has a doorway to the kitchen. Should draw it right here. Okay. Kitchen. Sorry. The kitchen has a doorway to the living room. There we already have that one sketched in. The kitchen has a doorway to the dining room, which we have right here, and the kitchen has a doorway to the outside. So we'll sketch that in. Okay. And then finally, the bathroom only has one doorway, which connects to the dining room. We've already sketched that in. So there's our completed graph. Let's look at another example, a graph representing border relationships. The map shown in this figure shows 5 counties in central Pennsylvania. We want to draw a graph that shows the counties that share a common border. Okay. Explain your choices for vertices and edges. Okay. Try to keep this picture visible for us. In essence, the common borders are what connects the counties because you cross the border to get from one to the other. So we want to represent the counties with vertices and the common borders with edges. Okay, so let's do V for Venango County, F for Forest County, E for Elk County, C for Clarion County, J for Jefferson County. So then we want to take each county one at a time and see which borders each county shares borders with. For example, Venango County shares a border with Forest County and Clarion County. So we will draw those as edges. Forest County, Clarion County. Forest County shares a border with Venango County, Clarion County, Jefferson County, we'll sketch that one in, and Elk County. So we'll sketch that one in, okay? Elk County shares a border with Forest County. We've already drawn that one in. And Jefferson County. Draw that one in. Jefferson County shares a border with Elk County. and Forest County. We've already sketched those edges in, but then also Clarion County. So we'll sketch that in. And then Clarion County shares a border with Jefferson County. We have that edge drawn in. And Forest County, we need to draw that one in. And Venango County. So let's see, do we miss anything here? I don't think so. So we've gone through each county one by one, and we've drawn a border an edge to represent each border, each common border between the counties. And that's our resulting graph right there. Okay. All right, let's look at another example. A graph representing city streets. A plan of streets in a neighborhood is shown in figure 13 in this figure here. Draw a graph for the neighborhood. We want to use the intersections of the streets as vertices and the streets as edges. Okay. So we want to place a vertex at each point of intersection of any two or more streets. Okay. And then connect the vertices with edges that follow the streets, basically. Okay. Okay, so I'm going to just place a dot at the intersections on the actual map here, right? So there's an intersection there, there's an intersection there, intersection there, intersection there, intersection there, and there, and there, right? So, oh, and then we missed one, right? So my graph will have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 vertices, and then the roadways represent the edges, right? So just sketch this in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are my edges, or my vertices, sorry, and then the edges are represented by the roadways. Okay. Just something like that. Okay, so that's the idea. Let's get in here and talk about some more concepts, equivalent graphs. If we glance quickly at the two graphs in figure 13, 14 here, the question is, are they the same? So what we'd want to do is we want to basically check to see, do they share the same number of vertices? We have vertices A, B, C, and D. And are the connections the same, right? So vertex A connects to B, C, and D. Both here, B, C, and D, right? And kind of check the connections for all of them, right? Vertex B connects to A, C, and D, both here and here, A, C, and D, and so on, right? So if you kind of go through carefully, what you'll see is that, yes, the graphs are the same. Even though they look physically different, they're really the same graph because they have the same vertices connected in the same way. The only difference is where the vertices are physically situated. So when two graphs have the same vertices connected in the same way, we call them equivalent. Okay, so these are equivalent graphs. So explain why the two graphs shown in figure 13, 14 are equivalent. Let me say this. Each graph contains 4 vertices. Okay. And they are, labeled A, B, C. Sorry, my pen is messing up on me again. Ah, gosh. Let's try something here. And D. Okay. And we would say also that in each graph, okay, every vertex is connected to each of the other three vertices. Okay. Okay. So the graphs have the same vertices and the same connections, so that means they are equivalent. Let's look at some more graph theory terminology. We say that the degree of a vertex is the number of edges that intersect that vertex. An even vertex has an even number of edges that intersect it, while an odd vertex has an odd number of edges that intersect it. Loops are considered to be two edges intersecting a vertex. This figure here shows some even and odd vertices. Here's an even vertex because it has two connections. This one is degree 4, right? There are 4 edges connecting it. Degree 6, 6 edges. Degree 1, degree 3, and degree 5. So these are all even vertices up here. These are all odd vertices down here. We say that adjacent vertices have at least one edge connecting them. In this graph here, vertex A is adjacent to vertices B and E, right? Because they're connected by an edge, but vertex A is not adjacent to either C or D, since there is no edge connecting C and D to A. Okay. Okay, we say that a path on a graph is a sequence of adjacent vertices and the edges connecting them that uses no edge more than once. When finding a path on a graph, a vertex can be crossed more than once, but an edge can be crossed only once. Okay, and in this figure here, figure 1317, shows a path on a graph. Just follow the arrows, right? The path starts at vertex B, then goes through vertices C, E, and F in that order. The path is then described as BCEF. A graph can have many paths, and a path doesn't have to include all of the vertices or edges. Okay. A circuit is a path that begins and ends at the same vertex. A circuit is shown on the next graph in figure 1318. Okay. It is given by starting at vertex A, B, C, E, and A, right? Begins and ends at vertex A. Okay. A graph is said to be connected if for any two vertices there is at least one path that connects them. In other words, a graph is connected if you can start at any vertex, follow along the edges, and end up at any other vertex without tracing an edge more than once. If a graph is not connected, we say that it is disconnected. Disconnected. Okay, figure 1319 shows examples of connected and disconnected graphs. Okay. These three graphs are connected. These graphs down here are disconnected. Okay. Okay. You can see they're disconnected because they have sections that are not connected by any edges. Okay. Okay. A bridge on a connected graph is an edge that, if removed, makes the graph disconnected. Okay. Figure 1320 here shows three graphs that have bridges. This graph, if we remove the bridge connecting B to E, we see that it makes the graph disconnected. If I remove the bridge connecting D to C over here, it would make the graph disconnected. Or down here, if I remove the bridge C to E or A to C, it would make the graph disconnected. Okay. All right, let's take a look at our next example, recognizing features of a graph. We want to use the graph in figure 1321 here to answer each question. List the odd vertices, list the even vertices, which vertex has a loop, are there any bridges, identify at least one circuit. Okay. Okay, list the odd vertices. The odd vertices are the ones that have an odd number of connections, right? So if we look at this carefully, we should see that vertex V, right, has three edges touching them, right? Vertex W has three edges touching it. And vertex X has three edges touching them, right? So those are odd vertices. And then also vertex Z, which just has one edge touching it. So that's also odd, right? So answer to part A here, we'll just say vertices V, W, X, and Z are all the odd vertices. List the even vertices, right? Vertex T has and vertex U have two edges connecting them. Vertex Y has four edges touching it. So these are the even vertices. Okay, so say vertices T, U, and Y. All right. C. What vertex has a loop? That would be vertex W, right? There's a loop at vertex W. Are there any bridges? So there are two bridges. One would be edge WY, right? If I remove WY, basically this loop over here would just be disconnected, right? So this is, so WY is a bridge, and then also YZ, right? If I remove YZ, it will make the graph disconnected as well, because it will isolate Z. Okay. So those are the only two bridges. Okay. Let's see. Two bridges. Those are WY and YZ. Okay. Identify at least one circuit. Okay, there would be dozens of examples for this, but one example is, one of many examples would be starting at vertex T, going to U, okay, and then going to V, and then going to X, and then going back to T, right? So that's just one example of one possible circuit, right? We'll just lay that down. So T, U, V, X, T. All right. All right, let's go on to kind of our final topic for this section here, graph coloring. If you look at examples of maps from earlier in this section, you'll notice a feature common to many maps. The individual states, counties, or countries are different colors to make them easier to distinguish. But how many different colors are necessary to make sure that no two neighboring regions have the same color? This is a topic called graph coloring. This was a topic called graph coloring was developed to answer this question, and it turned out to have many other applications. We'll return to the map question in a bit. First, let's define some basic terms, and then look at a more useful scenario in our world. A coloring, for a graph is a method of coloring all the vertices so that any pairs of vertices joined by an edge have different colors. The smallest number of colors that can be used for coloring a graph is called its chromatic number. Okay. All right. Anyone in the business world will tell you that meetings are about half of what they do, and scheduling meetings can be a real challenge. At one company, there are 7 different groups that have regular meetings, with many employee members of multiple groups. Finance, represented by F. Strategic planning, represented by S. Human resources, represented by H. Health, care, and wellness, represented by W. Employee relations, represented by E. Union negotiations, represented by U. And board of managers, represented by B. The graph in figure 1323 here shows relationships between the groups. An edge connecting two vertices means that those groups have at least one common member. The goal is to schedule meetings so that there's never a time when two groups with a common member meet at the same time. Certainly, this could be accomplished by scheduling 7 different meeting times so that no two groups ever have conflicting times. But is there a more efficient way? What's the smallest number of meeting times that will work? In terms of the graph, any two vertices that have a common edge represent common groups with common members. So we can turn this into a coloring problem by using colors for the vertices, making sure that no two adjacent vertices have the same color. This would represent a meeting time when someone has 2 meetings to attend. So let's let's try this. Let's go to example 7. So for the company described earlier, find the smallest number of meeting times that guarantee no time conflicts. And then which committees can be scheduled at the same time. Okay, so we're going to basically redraw the same graph, but we're going to color the vertices. So let's do this. We'll begin by coloring vertex F blue. Okay, so this is vertex F. Okay. So that means that vertices B, remember B and S here, cannot be blue because they're connected to F, right? So if they're connected, they can't share the same color. So, and they have to be different from each other, right? Because they're also connected to each other. So let's choose red and green for vertices B and S, okay? So we'll do, let's see, we'll do red. Sorry, let's go over here. This is red. Okay. And green. All right. So let's go ahead and connect those. All right. Okay, now let's go back up here. Vertex U right here can be colored blue, okay, which requires H to be colored green. Okay. Notice that it's connected to vertex B, right, which is already red. All right, so we can do this. So vertex U can be colored blue. Okay. This is vertex U. Okay. And then we have vertex H over here, which can be colored green. Okay, so U connects to H, B connects to H. Okay. Then vertex W is connected to B. Okay. So vertex W over here actually has to be blue. Okay. Vertex W is connected to B. Okay. All right. B, which is red, and also to H, right, which is green. So then vertex E can be either red or green. So let's make it red here. All right. There you go. Right, so basically we set it up so that every vertex is always connected to a vertex of a different color, right? And so any vertices that are of the same color are not directly connected to each other. Okay. Which committees can be scheduled at the same time? That was the second question here. The vertices that are the same color are not connected to each other by any edges. So those are the ones that do not have any common members. So vertices F, U, and W are all blue. So the finance, union negotiation, and healthcare and wellness groups can meet at the same time. Vertices B and E are both red, so the Board of Managers and the Employee Relations Committees can meet at the same time. Vertices H and S are both green, so the Human Resources and Strategic Planning Committees can also meet at the same time. Okay, let's look at another example. Applying graph coloring to maps. Use graph coloring to find the number of different colors that would be necessary to color the map in 1326 so that no states with a common border are the same color. Then color the map using what you learned from your graph. All right. So using the technique that we learned earlier in the section, we can draw a graph representing border relationships. Okay. Okay, so what we'll do is let's see. Let's start with Nevada, and we'll make Nevada blue. Okay, so we'll say blue. We're going to do vertex. I'm trying to figure out the best place to draw this so you can see the whole thing. Maybe over here. All right. Oopsies. It's not blue. Try again. Okay, so blue for Nevada. Okay. Nevada borders California, Arizona, Utah, Idaho, and Oregon, right? So none of those bordering states can be blue, right? Let's do Oregon, and let's make Oregon red. Sorry. This is Oregon, okay? Let's see. If we choose different colors for Idaho and California, neither of which can be either blue or red because they both border Nevada or Oregon, then we already have 4 colors. If we make them both green, then Arizona and Utah have to be different colors, but they can't be either blue or green. Okay, so this shows that at least 4 colors are needed. Okay. So let's see. Let's explore this a bit more. So what can we do? We could. Let's see. We have Nevada. Okay. Let's do. Oregon is red. Let's do. Sorry. We'll make California green. This is California. Okay. Like so. We'll make Arizona red. Oops. I've been using black for the actual edges, right? And Utah. We'll make yellow, I guess. It's kind of hard to see. Oopsies. That needs to be U for Utah. Okay. Okay, and then let's see. Nevada also borders Idaho, right? And we can make Idaho green. Okay, like so. Okay, so we have everything covered for Nevada, right? So Nevada borders, oopsies, again, I'm getting this messed up here. That is green, and this is I for Idaho, right? So Nevada borders Idaho, Utah, Arizona, California, and Oregon, okay? And notice that we don't have any two colors that are directly connected by each other, right? So that looks like that works okay. Then we know that Oregon and Idaho are connected, right? Idaho and Utah are connected. Utah and Arizona are connected. California and Arizona are connected. Oregon and California are connected, right? And then we still need Washington. And so Washington needs to be a color. So Washington borders Idaho and Oregon. So Washington cannot be either green or red. Let's make it blue. Okay, there's W for Washington. Washington borders Oregon and Idaho, right? So then you just want to kind of make sure that no two adjacent bridges are connected to each other, okay? Yeah. Yeah, so I think that's our completed map right there. Okay. If we were to kind of shade it in the actual map, right? Oopsies. I do something like this. There's Utah, right? Arizona, Oregon, right? Idaho, California, Nevada, Washington. All right, so that's the idea, right? That's the idea with graph coloring, is to explore concepts like this. So, okay, we'll explore these concepts a little bit more in the next section, but we're going to wrap up this video right here for now. Thanks for watching.